I will lay out the issue from the outset. The loss of information at our horizon is either an optical phenomenon or a physical one. If it's physical, people disappear by walking over the curve. If it's optical, people disappear by the angular resolution limit of the observer. Option 1, the ground is brought to your eye level. The person disappears from perspective by walking straight away and vanishing bottom first, from things getting smaller with distance and an angular resolution limit. So in the diagram, the floor is brought up to your eye level. The person gets smaller with distance and eventually disappears through the angular resolution of the observer. Option 2, the eye is brought to ground level. The vanishing person is represented orthographically without regard to perspective, and your focus continually shifts downward to observe them going over a curved surface and vanishing at the same rate that happens to be the angular resolution limit of the human eye. So again, in this situation, your eye line now moves downward to continually shift and adjust for a person walking over a greater amount of curve as they walk away and become smaller. So after reviewing the above options, we will see how the optical angular resolution limit of the human eye was replaced by the physical curvature of Earth. We will then use the angular resolution limit to calculate a sphere with a radius of 3,959 miles to 3,978 miles. At the end of the series, you can decide which version better represents reality. For our assumptions, first, the perspective changes with the observer and the observer position. Objects get smaller with distance. Small objects disappear from vision, and the horizon rises to eye level. So for our objectives, this will be a 6-part series. We will possibly expand on things in the future, but for now this will be 6 parts. The first part will concentrate on angular resolution, what it is, what it defines, and how we likely see the world. And then the second part will be the world that we were given, the world that is proposed, and some biblical significance for why that is. So I'll go through them briefly here. The first part in this series is going to be the version that you're watching right now, which is to define one-point perspective, explain the basic optics of a lens system, and demonstrate the horizon at eye level. The second part will be perspective changes with the observer, and how your perspective alters with different heights. We will then go through in part 3 the angular resolution, Airy patterns, Airy disks, Rayleigh's criteria, diffraction limit, differential angular compression, and the resolution of images above and below the vanishing line, angular size stability of the sun and moon, the cause of a sunset, the importance of Polaris with regard to distant vision and position, and the effects of magnification on perspective and resolution. In part 4, we'll discuss the inferior mirage and the horizon, refraction across bodies of water, and a summary of angular resolution. And then in part 5, we'll get to the world that is proposed. We will discuss a little bit about Airy's failure, the axial tilt, and the human eye vertical field of view as a means to derive Earth's radius. We will also discuss the derivation of Earth's radius by the extrapolation of the angular resolution limit of the human eye, and a derivation of the parabolic drop rate within perspective as 8 inches per mile squared. And finally, we will close on empirical evidence of deception and biblical significance. So again, this is the first part of the series, so we will define one-point perspective, explain the basic optics of a lens system, and demonstrate the horizon at eye level. So we'll start with our lens or our eye looking at a block. 2 light rays are sent to our eye. We know that we see the world through a spherical geometry due to the shape of our eye, but even at relatively short distance away, spherical geometry assumes planar representations, and so in that respect, the use of planar geometry is accurate for illustrative purposes, and video links are in the description. We can add another object and create an alternating pattern of any kind or substance. We can assume for the moment that this is an orange and blue paint that are on the wall, and we are looking at that. This side-on view is termed orthographic, when we're kind of looking at the side of the head of the observer and modeling an image. We can add a floor to our paint on the wall and a ceiling, and you start to see a corridor develop. We can shorten the distance to the object. The angles at which they are seen increase outward. So the yellow angles are wider than the green angles, and the green angles are wider than the red angles. We will make our paint stripes within this corridor roughly 10 foot in width going down the corridor. So again, you can see how the yellow angles are slightly wider than the green, and the green are slightly wider than the red. And again, these are the light rays that are entering your eye from this object. If we zoom in, you can see that the closer the object has more divergent visual field lines than the more distant object. So the more distant paint on the wall is those red, green, and yellow lines that are more acute, extending out further at that 160 foot and 170 foot range. And then as we go closer into that 10-foot range, you can see how wide those angles are and how different they are. And if we zoom in on any one of those angles in the middle, you can see the effect as well. So assuming that those middle angles are extending way out far to orange and blue paint, further out to the right of the picture of the screen, say several hundred feet, those would be even more compressed. So again, the further the object, the more compressed and small this angle is as it approaches your eye. So note that these are parallel lines. If we lay some parallel lines down in our corridor that are parallel to the floor and the ceiling, we will start to see how this will become our perspective view. So again, all these are parallel and perpendicular lines to one another. The paint stripes are perpendicular to the ceiling, and then we have some parallel lines that we placed going down parallel to the floor and the ceiling. So when we render this to our perspective view, what we see may not represent this orthographic reality. It may not look like this. And these lines will not appear parallel, they will appear to converge. So keep in mind that the floor and the ceiling do run parallel, as well as any other line along the side that is parallel to the floor or ceiling. It's still a parallel line. It just may not look that way when we put it into perspective. So we can also progressively shorten the distance to the object. We can just keep adding paint, and so we can say we have 6 columns now worth of paint, and we're going to do the same thing. We're just going to shorten the distance to them, and you start to see how these light ray patterns start to develop, getting more and more divergent as the object gets closer. So for this illustration here, try to remove the paint from the wall just for a second and concentrate on the light bulb. That light bulb is sending off rays that get more and more divergent as they are traveling outward. But our eye, the convex lens in our eye, is also converging those light rays at the same rate. So even though the light is expanding possibly exponentially outward to our eye is then converging them exponentially back down to represent the linear world. So the information at the periphery does change at a faster rate than at the center, but our lens takes care of that and converges those rays at a rate proportional to that divergence, and we view the linear world. So if you reverse the information that is being converged by the eye, and I just reverse those lines around and have them coming off from the light source, you start to see in general terms what our eye is trying to converge back again to represent reality. So down in that third pic from the bottom, you can see all those light rays that are getting extended outward towards us. We are then taking all those light rays and converging them back again to get a picture of our world. So these oncoming light rays are what we converge to form our perspective. We will cover these transversal and orthogonal lines in a bit. The transversal lines are those rectangular uh, square lines in the lower right diagram, and the orthogonal lines are the radial lines extending out from the center. We'll cover those later, but note that if the outer ray is diverging more, it is converged more by a proportional amount by the lens. That's the big takeaway here. For the bottom diagram, that's called the inverse square law for light. So just remember that this can be for the left and right walls looking top down on a person, or the ceiling and floor looking at the side of their head. In other words, you can be looking down on someone and have this same view, or you could be looking at the side view orthographically. All things are parallel and perpendicular to one another, and the angle between the walls and the ceiling is 180 degrees. So the light entering the eye is again spread out to us by the inverse square law, and we are then converging that light back again. So again, if an outer ray is spreading out more and it hits the lens at a greater angle, it's then refocused by a proportional amount and the image remains linear as it exists. So image size or height h becomes inversely proportional to the distance away, and we can write that as follows: h is proportional to 1 divided by the distance. So if we double the distance, the size reduces by 1/2, and so on. As we'll see with distance, we focus light across a larger focal length and limited aperture. So we limit the rays with which we are viewing the object, and there is an angle at which they become so close that they are interpreted as a single ray. And for the human eye, this angle is about 1 arc minute, or 0.02 to 0.03 degrees, and it represents this vanishing point of our vision, since we must have 2 light sources to construct an image, and we'll cover that later. Just realize that we can't see forever, and there is a vanishing point where information is simply too compressed to make out. So again, in the diagram here, we have some light coming off of a building, spreading out exponentially through the inverse square law. We are trying to reconverge that image on the other side, and if it is too far away and we are resolving that building with a extremely small angle, we won't necessarily see the building. It will be beyond the vanishing point, and we will only view the paint in the walls. So we would interpret the building as that central circular dot potentially in the middle, and we may not see it. So that's just how our vision works. So the light is radiated, is then converged at the same rate, and what we interpret is there at the bottom. So for illustrative purposes, we can view this another way. When we rotate the floor and ceiling until they meet along the center line, or we'll call it the eye line, the point that they meet along this vanishing line is the vanishing point. And recall that while a near column may appear larger than a further column, they both are the same. And 10 feet is still 10 feet, even though one is bigger by being closer than another, which is further away. So I'm trying to represent that here by converging the floor and ceiling in that bottom diagram. I do so by basically rotating those black lines from the eye being the vertical field of view at around 65 to 68 degrees, rotating them to that amount, and then the ceiling and floor essentially rotate down to meet a central point or vanishing point. And then as you do that, the angles get smaller and smaller as they get further and further, and they get wider and wider as they get closer and closer. And so you can try to represent some of the paint in the walls as they would represent in that kind of a diagram. So I'm having them get a little bit bigger and bigger as they get closer to your eye. So again, it's just for illustrative purposes. It will become important down the road, but for now I just want to lay the framework for that. So objects linearly scale inversely proportional to the distance. So to prove this to yourself, measure out the distance in a space like a hallway or a corridor, and take a series of pictures at evenly spaced distances to an object, and you will see that as you double the distance, the size decreases by 50%, double it again, and it reduces another 50%, and so on. So you can do this with a hallway and a door, which is what I did here. Again, double the distance, half the size. So this 80-inch door changes apparent size with distance. So if you look at my corridor here where I compress the ceiling and the floor down the lower left to a vanishing point, you can see that the door may be a certain size closer in, but as it gets further out, the door is going to get smaller and smaller, and it does so inversely proportional to the distance. So at 120 inches away, it's going to be a certain size, represented by the yellow line. If I get 240 inches away and I double the distance away, the size will reduce by half. And if I get 480 inches away, it reduces by another half per. So it becomes 4. So we can rewrite our formula to compare these objects as a ratio. So height inversely proportional to the 1 over the distance for two different sets of distances and heights can be written as height 1 over height 2 is equal to distance 2 over distance 1. So the 80-inch door is half the size at twice the distance, or 1/3 the size at 3 times the distance, etc. But the door is always itself 80 inches. Just keep that in mind. It's just perceived differently. So in general terms, we can now translate this model to one-point perspective to see how the vanishing line or the eye line creates a vanishing point. It is the limit to our visual world. Recall that angles expand exponentially by the inverse square law as they near you and are then exponentially converged again by the lens so as to retain their same proportions. If they depart at a smaller angle due to a further distance, they are then converged at a smaller angle and appear smaller. And we will cover that when we get to the optics of a lens. So again, up in the upper left there, that's just an orthographic side-on view of some light radiating outward towards us and us reconverging it back again. And again, as it expands outward, it's then reconverged at the same rate. We can then collapse the floor and ceiling to meet along a vanishing point and re-represent our paint along the walls getting bigger as it's closer and smaller as it's further away. And we can rotate that view around to get the one-point perspective of the observer viewing down our corridor as below. So again, the vanishing point is that point off in the distance, and recall that even though just like the door got further away, it got smaller, it was still 80 inches. So these 10-foot markings are still 10 feet, even though they are further away and smaller. So we'll now go into some detail on the vanishing point. We see through a convex lens system where light is inverted on our retina and transmitted through our optic nerves, and optic radiation inverted and reversed again in our visual cortex to appear as if upright. So I'll discuss a convex lens system briefly, then apply it to our vision. So light bends through a prism via a process called refraction. It's a velocity change of light within another medium such that the angle at which it travels is altered. So the higher the refractive index of the medium, the slower the light travels, and the sharper the angle the ray takes as it travels through it. So we can make our arrows that are traveling through our prism on the lower left some kayakers instead to get a better understanding of what's going on. And let's say they connected themselves with a metal bar and they are going through this prism, which we'll think of as like some thick sludge. So, and this will be our refractive medium. So as the kayakers approach, the kayaker on the bottom there, he hits the thick sludge earlier, so he's going to get slowed down, and the top kayaker, he's going to be still continuing to go faster. So the metal bar is going to swing in line with the thick sludge, essentially. And then it's going to travel straight through that thick sludge because all of them are going to be going at the same rate until that top kayaker hits the good water, we'll say, or the non-sludge water first, and he starts going faster immediately. But meanwhile, the bottom guy is still stuck in that sludge, and he's going to go slower. Eventually, though, he's going to get out of that sludge too, and the whole light ray is going to travel down one more time. So that's how light refracts through the prism. And looking top down on the kayakers, the ones on the bottom hit the sludge first and go slower, and the ones on the top continue on. So the line of them is bent toward a new downward path, or whichever vector you're looking at. So if we invert the prism, the opposite occurs, and they will be going the other direction. So we can add the prisms together in such a way as to create a lens. So a lens such as the one in your eye or in your camera will converge all light no matter its entry point to a focal point. So essentially, if you have the same amount of thick sludge, and since light is traveling at the same rate through through the lens system equally, top and bottom, the light will converge at the same point on either side of the lens. If you shine it through one way, it converges to a focal point in front, and if you shine it through the other way, it converges to the focal point in the back. So this lens is a convex lens on each side. We call it a biconvex lens. So we can create another focal point on the other side, just like we talked about. We can then simplify our prisms to a more standard lens and draw our focal points f1 at a given distance from our lens d1, and double that distance for a second focal point f2 at a distance d2. And then f2 prime and f1 prime just represent the focal points on the other side of the biconvex lens at the same distance, just on the other side. So from Abbe's criterion, we know that we need two incident rays to create an image. Again, vision is contextual. You need to have two light rays going through the focal points that then reconverge on the other side of the lens in order to reconverge that image and to create an image. If you do not have those two crossing rays at that intersection point, no image forms. So if we put an object in front of the lens, the rays of light must enter by their respective focal points, or again, the image is not converged or properly resolved. So for simplicity, the first ray off the top of the tree, we'll say, goes through f1 prime in front of the lens, and the second ray off the top of the tree goes through f1 behind the lens. And where they cross over is where a real image is formed on the retina. And it's always inverted because it is a convex lens. That's just how convex lenses work. So the visual cortex then takes that information and reverses it back again so that we perceive, in this case, a tree as being right side up. But remember that it's actually inverted on our retina. So I don't want to get into the physics of lenses too much, but the image is inverted and smaller on the other side of the lens if it's beyond f2. Or f2 prime in this case. So if the image is at a certain distance beyond f2 prime, then it will converge inverted on the back of our retina, somewhere between f1 and f2. So if I pull back farther beyond f2 prime, it gets smaller and smaller and smaller. This tree, as I move it out to the left, let's say, further and further, it's going to get smaller and smaller on the back of our retina. And you can see that effect as we have these two trees compared here. And you can see how they would create a small, the further tree creates a smaller image. So again, we will not discuss lens problems where the lens is concave, where the image is inside f2 prime, because we see the world at a distance beyond f2 prime. Recall that f1, or just know that f1 represents about 1.6 centimeters. So as long as you're focusing beyond about 3.2 centimeters, or about 32 to 35 millimeters in front of your eye, the world is viewed as depicted. So again, we can now place this diagram within our optic system, and you can kind of see how this works. So the lens is the lens of our eye, or the lens of a camera, and the f1 behind the lens near the retina is where the light rays converge, and they converge somewhere between f1 and f2 if the object is beyond f2 prime on the other side of the lens. So the rays then, again, they diverge and they hit the retina or camera sensor with an inverted image that is again smaller with distance. So this is not a totally passive system. There is kind of an active component to our vision. We do have some ability to manipulate this incoming light, and there are three main ways that we focus near and far. The first is the convergence of the eyes themselves via the extraocular muscles. And the second is the stretch and relaxation of the lens via the ciliary muscles. And the third is the constriction and dilation of our pupil or aperture via the iris. The relaxation of the ciliary muscles makes the lens more convex, and as it bulges out, the pupil dilates. The contraction of the ciliary muscles makes the lens less convex, and as it flattens, the pupil constricts. Think of the pupil as just kind of laying on top of this lens, and as the lens gets kind of fatter and bulgy in the middle, the pupil will dilate. As the lens gets flattened out and straighter, the pupil gets constricted. And this is the Helmholtz theory, and there are other theories for how exactly this occurs, but regardless, when taken together, these three effects discussed are the accommodation triad for near and far vision and how we can manipulate this incoming light. So near vision is characterized by a more convex lens and a dilated pupil, and far vision is characterized by a less convex lens, a flatter lens, and a constricted pupil. So I'm just depicting that here. Again, the accommodation triad, extraocular muscles, your ciliary muscles, and their effect on the lens, and the secondary pupil dilation that occurs. But we can't manipulate this light and accommodate things forever. Again, going back to our lens diagram, with distance beyond f2 prime, a real image from converged light is formed on the sensor, but as the image extends beyond f2 prime, there is less refraction occurring of those incident rays. So as kind of an illustration to this, the central light ray is not refracted as it passes through the convex lens. So as we go far out beyond f2, you can see how the central ray will approach the ray through f1 prime. They'll get closer and closer. That blue central ray will get closer and closer to that ray that's extending from the top of the tree through f1 prime. So as we'll see, image integrity starts to break down and light rays are viewed as indistinct at a certain point. The lens convergence is at its minimum, and we reach a limitation on the system based on the manner in which it entered. And as we'll see, the pupil diffracts the light and the lens converges it. So when the lens can no longer converge the image, our image will remain subject to diffraction and reach a diffraction limit or an angular resolution limit. And we'll cover that in quite some detail. So as you can see, this angle here that's represented with this orange triangle, and I have these three trees at various distances beyond f2 prime, and the angle is getting smaller and smaller as those light rays are going off and have to converge through f1 prime to create the image. And you can see on the back of the retina there, those light rays as they converge, they're creating smaller and smaller trees essentially in the background or in the back. So again, as these rays merge and the angle gets smaller with distance, our vision becomes diffraction limited and a horizon line forms. This occurs at the angular resolution limit angle and for all angles less than that angle until the horizontal eye line. So in other words, there's a certain line or a certain angle at which an image won't be resolved, as we'll see, and any angle that gets smaller than that, you still just won't see it. You'll see it as though it were essentially a 0-degree angle. There will be nothing resolved at that point. So with this in mind, let's go into some detail on how we see the world. So up to this point, we've been equidistant from our ceiling, floors, and walls. Objects on either side of the vanishing line compress and expand relative to one another at the same rate. So again, we're right in the middle of the corridor, as we'll see with the next few parts. We'll see how that gets changed when we start to change our observer height. So if my eye is in the middle of the corridor, the wall, ceiling, and floor will all compress and expand linearly and equally proportional as I move near and far. Likewise, a near object in the middle of my eye line remains in the middle as it moves away, and it diminishes in size proportionally in all dimensions. So again, if I just put a box straight in front of my vision here and it extended itself, went further away from me, straight away down the middle of this corridor, straight in line with my eye line, it will proportionally get smaller in all dimensions and eventually disappear. So again, this is how we model a 3D world in 2 dimensions. So the vanishing line, again, is the point at which information is lost due to too small an angle, and this line is always perpendicular to the back of our retina, and this is important. The horizon is always at eye level because it is our eye line. It is optical. It is the point where the resolution angle is so small we perceive it and all angles less than it essentially as a 0-degree central angle or a straight eye line. This angle can occur 360 degrees around our eye line like a cone, but for simplicity we will model it just above and below the eye line. And these small resolution angles and any information within them represent our horizon. The horizon is the midpoint of our vision. So anything below the eye line, like a floor, is always the lower 50% of our visual field. And anything above our eye line, like a ceiling, is always the upper 50%. Same for the walls to either side of us if we had them. So if the ceiling were tremendously high, as we ascend in height, our personal horizon is always the point at which the top 50% of our vision meets the bottom 50%, or commonly where the sky meets the ground. As we'll see when we get closer to the floor, more and more of that floor is compressed into that lower 50%. So if we were to rise in height, if the sky and the ground remain in the middle of our eye line throughout our ascent, the ceiling and floor have remained essentially parallel to one another throughout that time. Just like when we are in a corridor and the ceiling and floor are orthographically parallel. So just quickly, as a thought experiment, if you lived on a sphere and rose to any height above the ground with your eye line parallel to the ground, the horizon would drop away from the midpoint of your vision with any rise in height. And we'll cover the observer height later, but as you can see, when photographing the horizon and using the same reference points, the horizon remains constant from 30,000 feet to 300 feet. The observer does not tilt down to keep the horizon in center frame, which is again what you would have to do if it were a curved surface that you were standing on. So again, here in this frame here, you can take a series of photographs from a plane using a wing marker or using a wing as with several markers along it, and you can standardize those markers and you will see that the horizon remains the same from 300 feet up to 30,000 feet. So again, just picture yourself atop a large sphere and raise yourself upward. As you ascend, your horizon would get further and further away, but it would also drop further and further below you. In order for you to keep the horizon at the center point of your vision, you would continually adjust your vision downward to view this new lower and further horizon. This is why the horizon rising to eye level is so important and goes to the heart of the two horizon options presented. Either the ground ascends to eye level or your eye level constantly adjusts to descending ground. So for airplane observations, you can tape your phone to the window, set it within the window the same way each time. Sometimes if you're on an exit row, there'll be like a little outjet piece that will, like the handle for the door, and you can set your phone on that to standardize the phone however you want to do it. But you do kind of need a view of the wing because you need to assure that there's not this lensing effect that can occur when in certain airplanes. So again, these are just some examples that I've done several times, just going up with various distances. You can see again using the wing markers that the horizon remains the same throughout your ascent, and it does not drop away from the center point of your vision. And again, that would have to occur if you lived on any kind of curved surface. It would, with any amount of height, it would start to drop away. So again, this is that lensing effect I'm talking about. Airplane windows usually have three panes. The first one is an inner plastic material. The middle and outer panes deal with the cabin pressure. That inner pane is just kind of a protective layer. So you'll sometimes see pressure relief holes between the panes. Sometimes you won't. It depends on the plane. But regardless of how pressure differences are relieved, since cabin pressure is significant at high altitude and decompresses with every single landing, there is sometimes a bulging of the pane such that it acts like a convex lens with increased cabin pressure. In other words, the higher you go up, the more convex the window becomes because you're getting greater and greater cabin pressure on the inside. So this is not always the case, but when it does occur, you will notice that the horizon drops and the wing is brought proximal by the same amount. So when the wing remains constant, the horizon will remain constant. And you can simulate this effect for yourself with a cooking lid or some other convex lens. You can see on the example in the lower left, you can just place the cooking lid against some markers, and you will see that in this case the backsplash stone, the horizon does appear to drop, the red line there, but at the same time the stovetop markers are brought proximal. So you will notice this in the plane as well. Here in the middle picture, you can see that the horizon does appear to drop relative to the window markers that I put down there. But you will also notice that the wing markers are also coming proximal and more proximal with height and with cabin pressure. And then on the lower right, there's another example of it where again you have a horizon line, but it does appear to drop in relation to the wing. But if you look at the markers on the wing, that wing has been brought proximal to your vision by roughly several feet. And there's another effect here, which is the blue line, which is this wing rise effect, which I'll go over here. But again, the horizon is brought lower with lens convexity, and wing markers are brought proximal at the same rate. So make sure you're keeping that in mind when you're doing these observations. So again, that wing marker, so you may have noticed that wingtip rise. This is common to wing construction and helps the wing adapt to air pressure changes. So if you see this used as a proof of horizon drop, keep that in mind. Wings rise in flight, the horizon doesn't drop. So in summary, when these effects are taken into consideration, you will see the horizon rises to eye level. And these are just some examples of some what these wings are capable of, and some practical examples of what they commonly do in each and every flight. So you can see this Boeing landing on this airstrip here on this runway, and you can see the amount of flex that's just in the wing, just from the few feet difference of landing there. And you can see this other one on the lower left, same thing, where it's on the runway, it's about to take off, and the wings, you can't see the tip in that photo. The wing is bent downward a little bit to the observer, and as the plane rises in height, you can see that the distal, or the more further aspect of the wing, is brought higher. Lastly, it's difficult to apply this same kind of leveling to high altitude balloons because it's difficult to assess when they are actually level. Video links in the description to some great high altitude balloon footage, roughly 18 of them so far. So the counter argument is that while the horizon may appear to be center frame, you can't say that you aren't looking down at it. That's the counter argument. And also something to keep in mind, the sun can light portions of the Earth and make it appear to look like a curved surface at high altitude, but with scrutiny, and as the balloon camera turns and you view the opposing horizon line, either lit from moonlight or anti-crepuscular rays, you will see the horizon remain the same shape as it was at low altitude. And again, the sun does create somewhat of a like a disc pattern extending out radially from itself at very high altitude. And you will see this if you're not careful while looking at some of these images. You will not notice this effect. And so I've tried to kind of show that for you down in some of these high altitude footage screenshots. So when you standardize this image, as the balloon camera turns around, you will see that again, you're not looking at a curved surface, you're just looking at what's being illuminated by a radial pattern of the sun. So also note that the effects of a fisheye lens and barrel distortions can occur. So you will find the same curvature rate in those cases at lower altitudes as you will at high altitude. So take, for instance, the Red Bull jump when he is at very low altitude over New Mexico. New Mexico is highly curved. When he gets up into high altitude, the curve of the Earth is the same as it was when he was barely over New Mexico. So again, as a summary of that, if the Earth is highly curved at a very low altitude, you know that that's not really how it looks, and it has the exact same curvature at high altitude. So again, it's actually flat low down, and it's actually flat high up. So cracking these codes is collaborative, so special thanks to all these great people who are doing great work every day, going out and doing observations and trying to analyze all this information and try to put it into some kind of coherent argument as to the true nature in which we live. So in the next video, we will discuss perspective changes with the observer and how our perspective changes when we change our height or get closer to the ceiling, get closer to the walls, get closer to the floor, and how our observations will change. So hopefully in this video we've defined one-point perspective, explained the basic optics of a lens system, and demonstrated the horizon at eye level.